So, as far as the sign flag is concerned, so as I said that it is used for indicating the sign of the data in the accumulator. So, after you have done some operation, if the accumulator content becomes negative, in that case the sign flag will be set to 1, and if the accumulator content is positive, then it will be 0. So, then the 0 flag. So, if the result is obtained is after doing the operation is 0, then this this 0 flag is set, and following an increment or decrement operation of the register. So, if you are doing some increment or decrement of some register, then also this 0 flag is set. So, for example, if I have got an instruction like say if I have got some instruction like say decrement B. Okay. So, this B register value will be decremented, and this decrement operation, if it is if the B register content becomes 0 due to that, then also the 0 flag will be set, or maybe increment operation. So, INR B. So, these are not on the A register. Okay. So, with the other registers also this is possible. Okay. Now, the carry flag. So, carry flag is set if there is a carry or borrow from the arithmetic operation. So, if the carry is generated, if you are doing an add operation. Okay. So, after doing the addition, if a carry is generated from bit number 7, or if you are doing a subtract operation, then a borrow may be generated from bit position 7. So, that way this carry or borrow, if it is generated due to arithmetic operation, then the carry flag will be set. Now, auxiliary carry. So, auxiliary carry flag is set if there is a carry out of bit 3. So, this I have already explained. So, bit position 3 onwards, if there is a carry due to either carry or borrow. Okay. So, either addition or subtraction instruction. So, carry or borrow is generated from bit 3, then this auxiliary carry will be set. Parity flag is set if the parity is even and is cleared if the parity is odd. So, 8085 it follows an odd parity structure. So, if the number of bits in the accumulator is even, then this parity bit will be set. So, that the total number of bits become odd, and if the number of bits in accumulator is odd, then this parity bit will be set to 0, telling that this is the number of ones there is already odd. So, this way this parity flag is going to be used, and some programs, so it can use this parity flag to know whether the number of ones in the accumulator is even or odd. So, we do not need to count, we need to check separately. So, we can just do a check on the parity flag and take a decision. So, if you look into the internal architecture, so we have already seen that general purpose registers, the accumulator and the flags. Now, next we look into the program counter. So, there is a program counter register PC. So, this is a 16-bit register, and this register is used to control the sequencing of execution of instructions. So, as I said that at any point of time, this program counter value, it tells me what is the address of the next instruction to be executed. So, it always holds the address of the next instruction, and it is auto incremented. So, as soon as we are accessing the next instruction, this program counter value will be incremented, and it will point to the next address from where the fetch has to be done. So, since it holds an address, so this is a 16-bit register. And there is a stack pointer register. So, stack pointer, this is also a 16-bit register, and it points to some memory location, and the memory this register points to is a special area called stack. So, this stack is used for holding the return, like in a high level language program. So, we are writing procedures, and we know that from some main routine. So, we can call a procedure, and from there from the procedure we come back to the main routine when the procedure is over. Similarly, when you are writing program in assembly language, then also you can write something called a subroutine. So, you can jump from the main program to a subroutine, and after finishing that subroutine you can come back to the point at which you have called that subroutine. Now, this return address has to be saved somewhere, so that at the end of the subroutine the processor will know where to go back. Okay. So, this return address is saved in the stack, and the stack pointer is used for pointing to the memory location where the last address has been stored. So, this stack is an area of memory that is used to hold the data that will be retrieved soon. So, this may be that return address, or it may be some parameters that we have passed from this main program to the subroutine. So, like that, so they can be retrieved from the stack, and it is usually accessed in a last in first out fashion. That is quite obvious, because whenever you are if this is your main program, and from here, so you have, this is the main program, and from here, so you have called a subroutine. So, this is the subroutine S1, and within the subroutine somewhere here you have called another subroutine, say S2. Now, when S2 is over, so you have to go back to this point, continue the execution, and then from this end, so you have to go back to this point. So, this is in the, so what, so whenever you are jumping from M to S1, so if this is the stack, in the stack you are saving the return address. So, you are saving this particular return address. So, let us call it star 1. So, star 1 is saved here. Then when you are going from S1 to S2, that return address, S1 return address is saved here, star 2. Okay. Then from when S2 ends, so we take out this value and come back to star 2. So, that is so the number star 2 entered last into the stack, but it is taken out of the stack at the earliest. So, that is how it is called last in first out. So, whatever entered last will be taken out first. So, this way we can this stack will say it can be used for doing some operation. There are some non programmable registers like say instruction register and decoder. This instruction register, this is a special purpose register, is also known as IR. So, whenever an instruction is fetched from the memory, so we have got this is we have got this the fetched pattern stored in the instruction register, and from the instruction register it goes to the decoder will try to identify the meaning of the instruction. So, this instruction is stored in the instruction register after fetched by processor, and the decoder will decode the instruction into IR. So, this instruction register, so this is being read and written, but from the user's point of view, so this instruction register is not accessible, because user will not be able to write something onto the instruction register or read the content of the instruction register through some program. Now, there is a internal clock generator circuitry. So, the externally, so we have to connect a clock some crystal. So, if we connect a clock with crystal 3.125 megahertz, then externally, so we see externally we connect this a crystal of 6.25 megahertz, and internally it is divided by 2. So, it becomes 3.125 megahertz. Okay. So, that is the clock frequency at which this 8085 will work. Then there are address and data buses. So, this address bus has got 8 signal lines A8 to A15, which are unidirectional. The other 8 address lines are multiplexed with the 8-bit data bus. So, this AD0 through AD7, they are bidirectional, and they serve both the purposes of the lower order address bus A0 to A7 and the data bus D0 to D7 simultaneously. It is not at the same time, precisely at the same time. So, so when this address data bus, this AD0 to AD7 is used as address bus, so it is not used as data bus, and similarly when it is used as data bus, it is not used as address bus. So, during the execution of the instructions, so these lines carry the address bits during the early part, and then during the later part of execution they will carry the data bits. So, basically if you are trying to access memory, so first you have to give the address, and while giving the address, so the address higher order part is in A8 to A15 and the lower order part is in A0 to A7. After some time, when the address has been noted by the memory, then you can withdraw the address from the address bus, and now whatever value this memory put onto the data bus, it comes as D0 to D7 to the processor. Similarly, if you are trying to write something onto the processor also, to the memory also, the same thing, the first you put the address. So, memory understands the address, then you withdraw the address and put the data bus content, so to be written. Okay. So, that is so now the part acts as the data bus. So, this in order to separate this address from data, so we can use a latch to save the value before the function of this bits changes. So, as I said that for initially for some time this A0 to A7 holds the address. So, in most of the memory design, so we will find that this address bus content has to be held continually. For that purpose, we can have some external latch by which this address value is latched there. So, this higher order address bus, so this has got this higher order address bits, they will remain on the bus for 3 clock periods. For 8085 this memory access takes 3 clock cycles. So, for 3 clock periods the higher order address bus will hold the value. However, as far as the lower order address bus is concerned, so it is only for 1 clock period this lower order address bus holds the address bits, valid address bits. So, what we need to do is after this 1 clock cycle, so this value is withdrawn. So, somehow we need to save this address somewhere, so that the memory sees continually that it has got all those address lines. But this for that purpose we have to have some external circuitry. So, we will use an external latch to save the value of AD7 to 0 when it is carrying the address bits, and we will use the ALE signal to enable this latch. So, this is the situation. So, you see that this A8 to A15, so actually this side we have got the memory. So, this side we have got the memory, it is this is the memory. So, these are the address lines. So, these are the address lines for the memory, and these are the this is the data line, fine. So, this address lines, so this higher order address bus, it has got A8 to A15, that is held continually for the entire read operation, memory read or write of memory access operation. However, this AD7 to 0, so it has got this address values A0 to A7 only for the first clock cycle, and for the first clock cycle this ALE signal is also activated. So, externally what we do, we use a latch, so that this when this ALE is high, this value of A7 to A0 gets stored into this latch. So, after that, after the first cycle this ALE signal is deactivated, as a result this latch becomes inactive and it does not change its value, even if this these lines input to the latch changes, since this ALE signal is low. So, latch will not put that value onto it. So, it will continually hold this A0 to A7 at the output. Now, after that this D0 to D7, so these are the data bus. So, either the memory will put the content onto this data bus, or the processor will, if it wants to write to the memory, so it can put the data onto this data bus. Essentially, so this process, as far as the memory is concerned, it sees this address 16-bit address line continually for 4 cycles, and it also sees for 4 cycles, and it also sees the data for the last part of the operation. So, as a result, so it can do this read write operation easily. So, this ALE operates as a pulse during the first clock cycle. So, when this 8085 is reset, so it every instruction access for the first cycle, so it will give a pulse on the ALE line. So, this will be able to latch the address, because A0 to A7 is also put onto this AD7 to 0 line. So, that the address will get latched, and then ALE will go low. So, address will be saved, and the line AD7 to AD0 can be used for other purpose, okay, that is for holding the data. So, this is known as the demultiplexing of the address data bus. So, in many processors, wherever we try to reduce the number of pins, so we can use this demultiplexing technique, so that pin requirement is low. Okay. So, next so overall picture is like this. So, if I have got this ALE here, 8085 here, and we are trying to connect a 1 kilobyte memory chip, okay, then this 1 kilobyte means, so this the address bus is 10 bits. So, this A0 to A9, so they are to be connected, and lines A10 to A15, so they total address generated by 8085 is 16 bit. So, out of that A0 to A15, they will go through some chip selection circuitry. So, in the previous, in some classes earlier, we have seen how to use these decoders to generate the chip select signals for various chips. So, some decoding logic will be put here, so that it will select this particular chip for some address range. Now, this A8 to A15, so they are coming directly from the 8085 as higher order address bus. Out of that, A10 to A15 is fed to the chip selection logic, and A8 and A9, so they will come to the lower side. Now, for the lower order address bus, lower order address, so AD7 to AD0, so they are passing through this latch, and this ALE signal is selecting the enabling the latch. So, as a result, A7 to A0 will be getting latched onto here. So, ultimately, so this A0 to A7, and from this side you are getting A8 to A9. So, total A0 to A9, so they are forming the address bus for the memory chip, and this D0 to D7, so that is the data bus, so it is there. Now, I need to generate the read write signals for the memory. So, this IO M bar line, so as I said that if M bar is low, then this IO, then this is a memory operation. So, this M bar and read bar, so if these two lines are inverted and then passed through a NAND gate, then that means, so this is the memory read bar signal. So, when the processor is doing a memory operation and it is doing a read operation, then this memory read bar line will be low. So, as a result, it is connected to this read bar pin of this chip, so that it is doing the read operation. Similarly, this write bar line and this IOM bar line, so they are connected into this gate, and it generates the memory write bar signal, and this memory write bar signal connects to the write bar signal of the chip. So, this way, this is the overall picture. So, if I have got more number of this is only 1 kilobyte memory chip interfacing that has been shown. So, if I have got more such chips, then this chip selection circuit will generate appropriate chip selection logic. So, rest of the thing will remain unaltered. Next, we will be looking into the most vital part of 8085, like as a user of the system, like how can I, what are the operations that I can do with this 8085 processor. So, that defines the instruction set of this 8085. So, 8085 is an 8-bit device, so it can have up to 2 power 8, that is 256 instructions. Out of that, only 246 combinations are used, and that represents a total of 74 instructions. And naturally, most of the instructions have more than one format. So, we will see that these instructions that we have, so they can be grouped into 5 different groups: data transfer, arithmetic, logic, branch, and machine control. So, these are the different classes of instructions that we have in 8085. So, we will look into these individual classes one by one. So, each instruction has got two parts. The first part is the task or operation to be performed. So, this part is called opcode, because it is operation. So, it is telling the operation to be done, and the second part is the data to be operated on, and it is called operand. So, we have got opcode and operand. So, any instruction can be divided into this opcode and operand part. Now, depending upon the instruction that we have, so number of operands may be 0, it may be 1, or it may be 2. So, we will see some instructions like that. So, say so based on the number of operands, the instructions may be classified. Instructions may be classified as 0 operand, 0 operand, single operand, or 2 operand. So, in case of 8085, we do not have more than 2 operands per instruction. So, it is at most 2 operand. So, 0 operand instruction, like say the halt instruction. So, this is a 0 operand instruction. So, no operand is necessary. Single operand instruction, I have already given a number of examples, like say add B. So, this B is the operand. Okay. Other operands are other operand, that is A is implicit for the instruction. So, you do not need to specify it separately. So, and this add is the mnemonic. So, that way this is a single operand instruction. So, 2 operand instruction, like there are instruction like which says that LXI H comma some 16-bit value, some 16-bit value. So, this tells that this 16-bit value has to be loaded into the HL register pair. So, we will see this instruction later, but here you see this is an example of 2 operand instruction, where H is the first operand and the 16-bit value that we have, that is the second operand. So, this way I can have different number of operands in the instructions. Next we will see how these instructions will look like. Okay. So, first category of instruction that we will look into, so they are known as data transfer operation. So, these operations they are useful for copying the data from source to the destination address. So, the instructions that are common is move, MVI, LDA, STA, etc. So, it is for example, we can have instructions like say move A comma B. So, this means the A register gets the content of B register, or say move D comma E, that means the D register gets the content of E register. Okay. Then there is MVI instruction, move immediate. So, it is like this MVI A comma 40. So, that means the A register will get the value 40. Okay. Then LDA, the format is LDA and a 16-bit address, is a 16-bit address like LDA say 2000 hex. So, this means the accumulator register will get the content of memory location 2000. Fine. Then STA is for it is just the reverse of LDA. So, STA 2000 hex, that means memory location 2000 will get the content of the accumulator. So, this way we have got this LDA, STA, move, MVI, this type of instructions, which is basically the copying of content of one register or memory location to another register or memory location. So, data between they can transfer data between registers like move A comma B, data byte to a register or a memory location like say this one MVI A comma 40. Okay. Data between a memory location and a register like say this one LDA we have seen, or data between IO device and the accumulator. So, there so that can also be done. So, this IO access we will see separately later. So, that is the IO device access can be done, but the data in the source is not changed. So, these are all copying. So, the source content will always remain unaltered. So, source content is not tampered with. So, these category of instructions, so they are known as data transfer instructions. So, this LXI instruction, so this 808, so this LXI instruction this provides an instruction to place 16-bit data into the register pair in one step. So, this LXI, the format is LXI register pair comma 16-bit address. So, it is load extended immediate. So, it tells that this LXI B 4000. So, this will tell that the 16-bit value 4000 will be put into the pair BC. Okay. So, this B will get 40 and C will get 00. The upper two digits are placed in the first register. So, this is a hexadecimal number. So, if I talk in terms of 8-bit value, so 40 is the first byte, 00 is the next byte. So, 40 is the most significant byte, 00 is the least significant byte. So, the most significant byte goes to the B register and the least significant byte goes to the C register. So, this is the LXI instruction. So, we can also think about memory as a register. So, most of the instruction in 8085 can use a memory location in place of a register, like say this instruction. So, this move M comma B. So, this memory location will become the memory register M. So, this M comma B. So, this tells that the content of register B will be copied onto memory location M, but what is the address? So, so when I say B, C, D, E, so we are talking about a particular register, but when I say M, so that is it is a memory location. So, this memory location address has to be told, and this address is implied, it is implicitly identified by the content of the HL register pair. So, it is like this, if I have got this HL pair has got the value say 1500 hex, that is H is having 15 and this is in H and this 00 is in L. So, if that is the situation, then if this is my memory this is my memory and this is the location 1500, and if the content so now in this instruction what will happen is that it will first go to the HL register and it will find out what is the content. It finds that the content is 1500 and then it will be copying the content of B register, suppose B register was equal to say 20. So, suppose B register was equal to 20. So, this 20 will be copied onto this location 1500. So, that is the meaning of this move m comma b instruction that we have. So, copy the data from register B into memory location, and which memory location? So, this is given by the 16-bit contents of the HL register pair, and HL register pair are treated as a 16-bit address and that is used for identify memory location. So, this is the way by which we can implement pointers. Okay. So, this HL pair, so it can be loaded with the address of the pointer. So, if I have, as I was telling, that if I have got a pointer p now, so we are writing like star p equal to say 10. So, that can be done in this way, that first this B register can be loaded with the value 10 by instruction mvi b comma 10, and then if this p happens to be the memory location, the address of p is say 1000, then this LXI h comma 1000 hex. So, that will be loading the HL pair with the value with this value, and then we will be doing this move m comma b. If we do move m comma b, then this content memory location 1000 will get the value 10. So, this is equivalent to this statement star p equal to 10. So, this is the way by which pointers can be implemented. So, if we are using this indirect addressing in the HL register using the HL register pair.